Hello, here we go. A strong form of induction and the well-ordering property. Okay, so what's the difference? So in the strong form of mathematical induction, essentially what you do is you prove the first case. You can read this, right? S n0 would be the first case, and then what you do is you fix an n, right? But you assume that for every k less than or for every k between n sub 0 and k, that s of k is true. Then using that fact, then we prove that Sn is true. And that would be enough to prove that Sn is true for every integer greater than n0. And where this comes into play is that, well, they're equivalent. I put a little note on that. But it comes into play when we here's the key, all right? When an element of a sequence is defined in terms of some of its predecessors, right? Not necessarily like in our other inductive proofs, it was always Sn was defined in terms of Sn minus 1, essentially. But here, if it's defined in terms of some of the predecessors, this becomes a useful technique, okay? For example, let's do this. Let's suppose that the sequence C1, C2, is defined by the equation C1 equals 0 and Cn equals now this is, you take this function here is basically defined as the integer less than the number n over 2. Okay, so it's Cn is C sub n, I guess we call it the floor of n over 2 plus n for all n greater than or equal to 1, greater than 1. Okay, so let's check this out. What does it do? So S2 is C sub 2 divided by 2 is 1, so it's equal to plus 2, right? So it's equal to C1 plus 2, so it's 0 plus 2, it's 2. C3, to calculate that, you calculate C sub 3 halves, right, plus 3. So that's equal to C sub 1.5, C sub floor of 1.5, but that's 1. Okay, so you get 3, 6, 7, etc., etc. Okay, so what we would like to do is to use strong induction to prove that C sub n is less than 2n for all n. Okay, so I guess the important thing is notice how in this C4, here's where we're not using C3, but we're using C2, right? So sometimes in this sequence, it's defined in terms of the immediate predecessor, but sometimes it's defined in terms of a predecessor that's not the immediate predecessor in the sequence. So here we go. All right, so what do we do? All right, now here's our solution. In this example, n0 in the equality is equal to 1, right? And because it says 1 is less than or equal to k is less than n. Okay, in particular, since C sub n is defined in terms of the C sub floor of n over 2, in the inductive step, we assume the truth of the statement for k equal to that number, whatever that is, right? That's what we're going to use it to be. We're going to assume it's true for that. Okay. Then what else does it say? Then because it says 1 is less than or equal to n over 2 is less than n, right? That's because that's true. So because n over 2 is less than n, yeah, we need that to be true. It follows that the floor of n over 2 is less than n. This is all pretty clear. Now, if n is greater than or equal to 2, then we have 1 is less than or equal to n over 2, so 1 is less than or equal to the floor of n over 2. Therefore, if n is greater than or equal to 2 and k equals the floor of n over 2, inequality 2.5.1 is satisfied. Thus, the basic step is n equals 1. We just have to prove it for n equals 1. Okay? And here we go. Here's the basic step. So C1 is equal to 0, and that's less than 2, which is equal to 2 times 1. So the basic step is verified, right? Okay, now here we go. Now let's assume that C sub k is less than 2 over k for all k with between 1 and n. And we want to prove that Cn now is less than 2 times n for n greater than 1. All right, well, since, and then we go through all this stuff, since 1 is less than n and 2 is less than or equal to n, thus 1 is less than or equal to n over 2. So we're just really showing that the number n over 2, we're showing this inequality is critical, that the value of the floor of n over 2 is somewhere between 1 and n, okay? And if we take k equal to that floor, then we see that k satisfies the inequality 2.5.1. So by the inductive assumption, we know that c sub n over 2 is equal to c sub k, which is less than 2 times k, which is equal to 2 times the floor of n over 2. Okay? Now, let's see what we get. Now, c sub n then is equal to c sub floor of n over 2 plus n. So then we can, it's less than by this inequality, right? We can replace that with 2 times the floor of n over 2 plus n, and that's less than or equal to, it could be all the way down to get rid of the floor function, but it's still less than or equal to 2 times n over 2, which is equal to 2n, and that completes the proof. So you will need to use this type of induction in various arguments through the course, so definitely do your homework and get all that situated. Now, the next thing in this section is the well-ordering property, and essentially it's required, and it's a very, very important property that basically says says that if you have a non-empty set, right, of positive integers, contains a least element. I think I must say that somewhere in here, right? Okay, so we need this fact, right, to prove the following very important theorem. And I'm just going to state this theorem. And this theorem we will be using over and over and over and over and over again, okay? It's the quotient remainder theorem. So it says if d and n are integers, and if d is greater than 0, then there exists integer q, the quotient, and r, the remainder, satisfying n is equal to d times q plus r, where r is strictly less than d. Furthermore, q and r are unique. That is, if n is equal to, if n is equal to this, then in fact, and if n is equal to this, in other words, you found 2 solutions of that, it turns out there's really only 1 solution, okay? I'm not going to go through the proof of that, but you want to become familiar with this because we're going to be using it time and time again. So, okay, hope that helps. Thanks. Bye.